Hello and welcome back. In this video we'll start section 6.1, which is all about normal distributions. And to begin with, we'll start with the uniform distribution, which is slightly different, but it's going to be fairly related. A uniform distribution is one in which all values are equally likely. So we can think of sort of a variable where all the values are spread evenly or spread uniformly across the whole range. And to give an example of what this might look like, maybe the wait times in a checkout line are uniformly distributed from 0 to 5 minutes. So meaning that when we think about how long will it take to wait in a checkout line, maybe at the grocery store, if it's uniformly distributed, then every wait time will be equally likely, whether it's 1, whether it's 2, 3, 4, or 5, they are all going to be equally likely. So the just imagine that this is a straight line, but so the probability distribution is just going to be a straight line. Everything is equally likely. Now, when I make a graph like this, what I want to do is I want to know what the height of this graph is. I can't draw this line coming across if I don't know what it means. And we're going to use the following principle a lot in this chapter. We want the following. We want area to represent probability. So when everything is equally likely, we want this height here to have a very particular value, and what we want is that the area of this rectangle that we can see, we want this area to represent the probability. So this is the area that stretches from 0 to 5. So every single wait time is going to be between 0 and 5 minutes. So the probability of this rectangle, the area of this rectangle, should be 1. So the area of the rectangle should be equal to 1, since this is the probability. Well, the length of the rectangle is 5. We can see that it stretches from 0 up to 5. 5 times the height of the function, or sorry, this graph. So we can see that this is going to be 1/5 or 0.02. And we're going to use this. We're going to use this a lot. Let's look at some examples of how we might use this. Let me erase some of these lines for a second. I'll come back and use this graph. So for instance, what is the probability that someone waits less than a minute? Okay. So if we come back up to the graph, we've got 1, 2, 3, 4, 5. So the probability that someone waits less than 1 minute should be the area of this rectangle. Again, we want area to represent probability, and the probability that someone waits less than 1 minute should be the probability that someone waits between 0 minutes and 1 minute. So we have this rectangle. We were able to calculate the height. The height should be the value that makes this rectangle have area 1. And then we can calculate this area. So if we're calculating the area of a rectangle, that's just the length times the height. So the probability, which is equal to the area, is just going to be the length times the height. So let's call it L times H for height. So what's the length of this? Well, it goes from 0 to 1, so clearly the length is going to be 1, and the height is going to be 0.2. So the probability that someone waits less than a minute is going to be 0.2. Uniform distributions are quite nice because they are only rectangles. Whenever we're trying to calculate the area of something with a uniform distribution, they're just rectangles. Let's do another one. So we've got, what's the probability someone waits between 1.5 and 3.5 minutes? Okay, this one will be a little bit harder. So we're looking for between 1.5 and 3.5. So we're going to look for the area of the rectangle between 1.5 and 3.5. Again, this is only a rectangle, so we just need to take the length times the height. So again, the probability is just going to be the area. And since we have a uniform distribution, the area is just going to be the length times the height. And the length this time we'll have to figure out. But this isn't too bad. The length, as in the distance between 2 points, is going to be their difference. So we'll take 3.5 and also subtract 1.5. This is going to be the length. This is the distance from 3.5 to 1.5. And the height, we said, was 0.2. Well, 3.5 minus 1.5, that's just 2. And 2 times 0.2 is 0.4. So all uniform distributions are rectangles. And when we want to calculate area, when we want to calculate probability, it's just calculating area, as here. And this is going to be a theme throughout essentially the rest of the textbook, is that probability is going to be equal to area. And specifically when we have a uniform distribution, the area is easy to calculate because area for a uniform distribution is just area of rectangles. Rectangles is going to be the height times the width, or I've been calling this length instead of width. So uniform distributions, pretty easy. Normal distributions is not going to be as easy. We're going to have to use calculators that will be built into StatCrunch. So we're not actually going to have to do very many calculations with this. So first of all, this chapter is mostly about normal distributions. And a normal distribution is a continuous distribution that's symmetric. So we have this picture down here, and we can see that it's symmetric. If you flip it over, it looks the same. It's bell-shaped. Okay, so it comes up in the middle, then falls back down. And it's given by this equation. This is a big equation. You are not expected to memorize this, and in fact, please don't memorize this. It won't exactly help. If you would be going further and taking more stats classes, more math classes, this is interesting. This is a very interesting function. But ultimately, for our purposes, once you've seen it, you can forget about the function. And this shape, the hump right here, the most common values are going to be at the mean. So the mean is, again, we write as the Greek letter mu. And the spread of the data, how wide the bell curve is going to be given by the standard deviation. So sigma is the standard deviation, and it basically tells you how wide is this bell curve. Now, in this section, we're not going to worry about the mean and the standard deviation very much, because we're going to essentially work with what's called the standard normal distribution. And what makes it standard? Well, we're going to assume the mean is always 0. So we're going to have an average everywhere of 0. And the standard deviation, essentially how spread apart the data is, we're just going to use 1 for this. So when we come back up to our bell curve, our mean is now going to be 0, and the standard deviation is going to be 1. So if I go 1 standard deviation above the mean, I'm at 1. If I go 2 standard deviations above the mean, I'm at 2. if I go 1 standard deviation below the mean, I'm at -1, and 2 standard deviations below the mean, I'm at -2. Again, 0 and 1 just make for a nice normal distribution. And these numbers down here, we will see pop up in different contexts, so it's nice to study just them in this section. Now, the probability for a normal distribution is still the area. Okay? So let's look at a couple of examples, and what I'll do is in the next video, I'll actually go through and calculate these. For the moment, I'm just going to draw some pictures to illustrate exactly what's happening. So let's assume that Z has a standard, standard normal distribution. And let's find the probability that Z is less than 0. So first things first, I like to draw pictures. I think these really help with normal distributions, even if my picture isn't very good. So we know that this normal distribution, the mean is going to be 0, and our standard deviation is going to be -1. So what we want to do is find the probability that Z is less than 0. So when I look at all these possible values for Z, what I want to do is I want to look at all the ones that are less than 0. So we're going to take 0, and we're going to look at all the ones that are less than 0, as in, for instance, -1, or -2, -0.3, -5, which would be way out here. Any value that occurs to the left is going to be less than Z. So the probability that Z is less than 0 is going to be this area. Now this is actually fairly straightforward to calculate, because we know the following fact. Normal distributions are symmetric, meaning exactly half, it's going to be balanced. Half of the area is going to be on one side and half of the area is going to be on the other. So if we knew what the total area was, 1/2 of it would be this area, but we do know what the total area is. So the other fact that we have to keep in mind is that the total area is equal to 1. How do I know this? The total probability has to be equal to 1. If you add up all the probabilities of everything that could happen, it has to add up to 1. So I know that what's just on the left-hand side of this, because this is perfectly balanced, this is symmetrical, that means that the probability that Z is less than 0 is exactly 0.5. So in this case, we could calculate this exactly. However, in other cases, it'll be a little bit harder. So let's assume that Z has a standard normal distribution, and let's find the probability that Z is greater than 1. Okay, so again, we'll draw ourselves a little picture of a normal distribution. And again, this is a standard normal distribution, so it's going to be, the mean is going to be 0, and then the standard deviation is going to be is 1. So here's our picture, and we want to find the probability that Z is greater than 1. So again, here is 1. All of the Z-scores that are bigger than 1 are going to be over here. So I'm looking for the area of this little shape. Now, this is where it's a little bit impossible to know exactly what this area is without doing a calculation. I can't use the fact that this is symmetric because, well, this is unbalanced. There's a little bit less area here than there is in the rest of it. So I'd actually have to do a calculation to come up with this, which I'll do in the next video. This last one, if we assume that Z, again, has a standard normal distribution, so if I draw a picture, and now I want to look at those Z-scores between -1.3 and 0.5. So again, we just draw a picture. There's negative 1.3, there's 0.5, there's the